Welcome back to Sleepy Orbits. Maybe tonight's one of those nights, the kind where sleep is taking its time and the big questions have found you in the dark. You're in the right place. Tonight, we're going after the biggest question there is. Every one of us asked it as a child, and no adult has ever answered it. If everything began with the Big Bang, what came before? Here is what almost nobody tells you. There are serious physicists at Princeton, at Oxford, at the great institutes of quantum gravity who believe that question has an answer, and that the answer is a universe. A whole cosmos before ours that expanded, slowed, turned, and came crashing back down, and whose collapse was our Big Bang. Not a beginning, a bounce, one beat of a heart that may never have started beating. You've probably heard that time itself began at the Big Bang, that asking what came before is like asking what's north of the North Pole. But here's the thing most people don't realize. That famous answer is not a fact. It's one hypothesis, and its main rivals are very much alive. In the bouncing universe, the question your 7-year-old self asked was never confused at all. There was a before. There may have been endless befores, and somewhere in the universe previous to ours, on some world circling some vanished sun, someone may have watched their sky begin to fall without ever knowing they were watching the birth of ours. Some of you were here for our night on Roger Penrose and the universe that never began. Tonight is the other road to forever, and by the end of it, the word beginning may never quite close around the universe again. One thing before we begin: if you fall asleep partway through, good. That's the point. In the morning, tell me in the comments the last thing you remember hearing, and if you make it to the end, tell me which part of the universe before ours stayed with you, and what you'd like us to explore next. If these nights help you rest, a like or a subscribe helps this channel more than you'd realize. Now, let's begin. Picture the moment you first asked it. You were small. Somebody you trusted had just explained with the confidence adults perform so well that the universe began with a great explosion billions of years ago, and that everything, the stars, the earth, you, came from that. And you did what every child does with a story. You reached for the page before page 1. But what was there before the explosion? And the adult paused. Maybe they said nothing. Maybe they said nobody knows. Maybe they changed the subject. Whatever they said, you felt it. That small, unsatisfying click of a door being closed rather than opened. Here is what you couldn't have known, lying there at 7 with the question still itching. The greatest physicists alive feel exactly the same itch. They have felt it for a century. The question you asked is not childish. It is arguably the question. And the flinch you sensed in that adult runs straight through modern cosmology. Because the strange truth is this: the Big Bang Theory, one of the most successful, most precisely tested ideas in the history of science, does not describe a beginning. It has never described a beginning. It describes an aftermath. It says, almost 14 billion years ago, everything we can see was compressed into a state hotter and denser than anything imaginable, and it has been expanding and cooling ever since. Run the film backward, and the universe gets smaller, hotter, denser, and then at the very first frame, the mathematics tears. The equations spike to infinity and stop meaning anything. That torn first frame has a name, the singularity. And here is the honest translation of what it is: not the moment of creation. The moment our theory breaks, the edge of the map, the place where the textbook quietly writes, "Here we no longer know," in letters most people never get to read. Everything you have ever been told about the beginning of the universe stops one frame short of the beginning. What actually happened at that frame, and whether anything happened before it, is genuinely, officially, gloriously open. And into that opening, tonight's idea walks, simple enough for the child you were to grasp instantly. What if the film doesn't tear at the first frame? What if, when the universe gets as small and dense as physics allows, it bounces? Compression becomes rebound, collapse becomes explosion, and the terrifying, impossible wall at the start of time dissolves into something almost gentle, a turning point. Our Big Bang, the fireball at the root of every star and every atom of you, becomes the crash at the end of a universe before ours, their ending, our morning. And if it happened once, why not before that? And before that? An endless breathing, expansion, contraction, bounce, with no first breath at all, no creation from nothing, no door closed on the child's question. Just before this universe, another, before that one, another still. Tonight, we're going to walk this idea from its birth to its funeral, to its astonishing resurrection, because it died twice, killed by the deepest law in physics, and then by the discovery that made this channel's last video possible. And it has come back in two forms that are alive, published, and being tested against the sky right now. Along the way, we'll stand on a world in a collapsing universe and watch the sky fall. We'll meet the quantum of space itself, and we'll end at a theorem that may forbid forever, or may not. But first we have to deal with the North Pole. The question is old enough to have embarrassed every age that asked it, and it's worth spending a moment with the most famous early attempt at an answer, because it will sound startlingly familiar. 16 centuries ago, Augustine of Hippo, philosopher, theologian, one of the great minds of late antiquity, faced a mocking version of the child's question that was already ancient in his day. What was God doing before the creation of the world? The joke answer circulating then, Augustine repeats it in order to reject it, was that the Creator was preparing hell for people who ask such questions. But Augustine's serious answer, worked out in his Confessions around the year 400, was this: the question is malformed, because time itself was created along with the world. There was no before, he argued, not because anything is being hidden, but because beforeness is a feature of the created order. Asking what happened before time is like asking about a color north of the rainbow. The world was not made in time, Augustine wrote, it was made with time. Hold that thought against the 20th century's most famous answer to the same question, given by Stephen Hawking and deserving of the same serious treatment before tonight complicates it. And you'll find the ancient bishop and the modern physicist saying, in their different languages, nearly the same astonishing thing. 1600 years apart, working from scripture and from space-time geometry respectively, both concluded, time is not the stage the universe was built on. Time is part of the building. Between the bishop and the physicist stands one more famous attempt, and it's worth a moment because it explains the peculiar dizziness the question induces, the reason it feels less like a hard problem and more like a trick being played on the mind. In the 1780s, Immanuel Kant put the question of the world's beginning at the head of his famous antinomies, pairs of propositions that reason seems able to prove both ways. Suppose the universe had a beginning. Then reason immediately asks what determined the moment, why then, and not some other point in an empty eternity, and finds no possible answer. Suppose instead the universe had no beginning. Then an infinite series of events has already elapsed before tonight, a completed infinity, which reason chokes on just as badly. A start is absurd. No start is absurd. Kant's conclusion was that the question overruns the equipment, that a mind built to organize experience in time cannot pronounce on the origin of time itself. He may yet be right. But physics, being stubborn, has spent a century constructing precisely the equipment Kant said we lacked. And tonight is a tour of the two ways it might escape his trap. A beginning that isn't an event in time, or a past that never completes because it was never a series with a first term. The answer goes like this. Before is a word about time. It only means anything where time exists. And time, in Einstein's physics, is not a great cosmic clock ticking outside the universe. It is part of the universe, woven together with space into a single fabric, space-time, that bends and stretches and participates in everything that happens. Matter tells space-time how to curve. Space-time tells matter how to move. Time is not the stage, it's one of the actors. And if time is part of the universe, then it may have been born with the universe. Follow the film backward toward that torn first frame, and perhaps what happens is not that we reach the first moment of time, but that time itself, as a concept, as a direction, as a thing, gradually ceases to be. Hawking's picture, developed with the physicist James Hartle, imagined the deep beginning as being like the North Pole of the Earth. Stand at the pole, and every direction is south. The question, what's north of the North Pole, isn't unanswerable, it's unaskable. The word north simply runs out there smoothly, without drama. In the same way they suggested, before may run out as you approach the beginning. The universe wouldn't have an edge in time any more than the Earth has an edge in the north. The child's question wouldn't have a hidden answer, it would dissolve. It is a genuinely profound idea, and notice what it grants. Even here, in the most orthodox answer physics ever produced, the Big Bang is not an explosion in time. Time is something that condenses out of the deep physics along with everything else. The pat answer you got as a child was a compressed version of this. There is no before because time began then. But here is what the confident retellings leave out. The North Pole answer is a proposal. It was never derived from established physics. It can't be, because it lives precisely in the regime where established physics has torn. To say anything about the first frame, you need a theory that joins Einstein's space-time to quantum mechanics, a theory of quantum gravity, and we do not yet have one that's finished and tested. Hartley and Hawking made an elegant guess about what such a theory might say. Other physicists, holding the same torn film, have made different guesses. The smooth pole where time dissolves is one guess. The bounce is another, and feel how differently the bounce treats the child. In bounce cosmology, time does not begin at the Big Bang at all. It runs straight through. The temperature spikes, the density hits its ceiling. Physics does extraordinary things, but the clock never stops and never starts. There is always a next moment and always a previous one. What came before the Big Bang stops being unaskable and becomes almost mundane. Before the Big Bang, there was a contraction, a universe on its way down. The question your 7-year-old self asked was, in this picture, perfectly formed all along, it just needed physics brave enough to answer it. Two visions then of the deepest past. In one, time is like north. It simply runs out smoothly at a pole. In the other, time is like a road over a hill. It looked like the road ended, but only because we couldn't see past the crest. Both are serious. Both have first-rate physicists behind them. Neither is proven, and they cannot both be true. Tonight belongs to the hill, because the bounce is not one idea. It's a family of them, with a century of history, a rise, a spectacular double death, and a modern resurrection. That is, quietly, one of the most interesting stories in physics. And it begins, like so much of tonight's channel, with a handful of people in the 1920s realizing that Einstein's equations were trying to tell them something enormous. When Einstein's general relativity met the universe as a whole, it did something the equations of physics had never done before. It offered a menu of possible universes. We've told pieces of this story on other nights, how the mathematics refused to sit still, how Einstein flinched, how a Russian mathematician named Alexander Friedmann trusted the equations and found, in 1922, the solutions everyone now uses. But there's a part of Friedmann's menu we've never explored, and it's tonight's ancestor. Friedmann deserves a face before he gives us his mathematics, because he is one of science's great might-have-beens. A Russian mathematician and meteorologist in post-revolutionary Petrograd, he was an adventurer as much as a theorist. He flew bombing missions in the First World War, and in 1925 he rode a weather balloon to a Soviet altitude record higher than 7 kilometers, taking measurements half frozen in an open basket. That same year, at 37, he died of typhoid. He never learned that the expanding universe his equations described was real. Hubble's proof came 4 years after his death. He worked out the possible histories of the entire cosmos as, essentially, a mathematical exercise in a starving city, published them in a journal Einstein grumbled at, and was gone before the universe caught up with him. What Friedmann found is that a universe filled with matter has, broadly, 3 possible fates, and which one it gets depends on a single cosmic quantity. How much stuff there is versus how fast everything is flying apart. Think of a stone thrown upward from the earth. Throw it gently, and gravity wins. Up, slow, stop, and back down. Throw it at escape velocity, and it just barely coasts away forever. Throw it harder still, and it leaves with speed to spare. The expanding universe, Friedmann showed, is the stone. If the cosmos holds enough matter, its collective gravity eventually halts the expansion, and then reverses it. Space itself, having stretched for billions of years, begins to shrink. Galaxies that spent eternity receding turn almost politely and begin to approach. The universe that opened like a flower closes like a fist, all the way down to a final, all-consuming compression that physicists came to call, with symmetry that's almost too neat, the Big Crunch. One universe, born in fire, dying in fire, a single breath, inhale to exhale. But the moment you draw that picture, a thought arrives uninvited. It arrived at essentially every physicist who ever looked at the closed solution, and it probably just arrived at you. If the universe ends in a state nearly identical to how it began, everything compressed, everything hot, everything dense, why should it stop there? If a Big Bang can come out of such a state once, why not again? Why shouldn't the crunch be a bang, the same event seen from the far side? Squeeze a universe to its limit, and perhaps, like anything squeezed to its limit, it rebounds. Bang, expansion, slowing, turning, contraction, crunch, which is to say, bang, expansion, and on in both directions, without end and without beginning. This is the oscillating universe. Even Einstein, in the years just after he gave up his static cosmos, was drawn to it. In 1931, he published work exploring exactly this kind of periodically expanding and contracting universe. And to understand why the idea glowed so warmly for so many, you have to see the battlefield it stood on. Because mid-century cosmology was a war between two pictures, and the oscillating universe offered weary combatants a third way. On one side stood the Big Bang itself, though it didn't have that name yet. Its prophet was Georges Lemaitre, the Belgian priest-physicist we met on another night, who called the first moment a day without a yesterday. A phrase so lovely it deserves to be said twice, slowly, at this hour. a day without a yesterday. Many physicists found that day philosophically unbearable. A universe with a first moment looked to them like physics writing a blank check to theology, a creation event sitting right there in the equations, unexplained and unexplainable. It didn't help suspicions that the theory's founder wore a Roman collar. On the other side stood the steady-state universe of Fred Hoyle and his colleagues, eternal, unchanging on the large scale, with new matter quietly created atom by atom in the gaps as the galaxies drifted apart, so that the cosmos always looked the same. No beginning, no end, no creation moment, except, critics noted, the continuous creation of matter from nothing forever, which is arguably a bigger miracle on an installment plan. Hoyle, a brilliant and pugnacious man, despised the rival theory so much that in a 1949 radio broadcast, he reached for a dismissive image for it. This idea that everything burst from a point in one great explosion, this Big Bang. The mockery stuck the way mockery does and became the theory's name. Science's most famous term of art began life as an insult. Hoyle went to his grave having accidentally christened the thing he spent his life fighting. The war was settled, as the best scientific wars are, by an accident, the stubborn microwave hiss in that New Jersey antenna, the afterglow, the baby picture, the light of the hot beginning itself. A steady-state universe has no hot beginning and should have no such glow. The detection of the cosmic microwave background in the mid-60s ended the debate almost overnight. The universe had undeniably once been a fireball. But notice the oscillating universe's exquisite position amid all this. It agreed with the winners about the fireball. Every cycle has one. The microwave background is simply the glow of the most recent bang, and it agreed with the losers about eternity. No day without a yesterday, no creation, no collar-wearing first cause. All the evidence of the Big Bang, none of the metaphysical bill. For a certain kind of physicist, it was the only picture that let you keep both your data and your peace of mind. And through the middle of the 20th century, it was many scientists' favorite picture of reality, held with something warmer than professional assent. You can hear the warmth in the writing of the era, because look at what the oscillating universe offers. The steady-state universe of the era needed matter created from nothing, continuously, forever. The one-shot Big Bang seemed to need a moment of creation, a first cause, an uncaused event, all the ancient philosophical machinery that physicists became physicists to avoid. But the oscillating universe needs nothing. No creation, no creator, no first moment, no unexplained ignition. Every bang is explained by the crunch before it. Every universe is the child of a previous universe. The chain of cause and effect runs unbroken through infinite time, and the embarrassing question, but how did it start, never comes due because nothing ever started. The universe isn't a thing that began, it's a thing that breathes. There was an older resonance too, and the physicists heard it. Cyclic time is one of humanity's most ancient intuitions. Hindu cosmology speaks of kalpas, world ages, billions of years long, in which universes arise, endure, dissolve, and arise again, wheel upon wheel of time. The Stoic philosophers of Greece taught that the cosmos periodically ends in a great conflagration. They called it ekpyrosis, out of fire, from which everything is born anew, again and again, eternally. Hold on to that strange Greek word, by the way. Set it somewhere safe. Near the end of tonight, 26 centuries after the Stoics coined it, it is going to reappear on the title page of a physics paper. And the fact that it does is one of my favorite small things in all of science. For a few decades in the middle of the last century then, it was possible to believe that the oldest human picture of time, the wheel, had turned out to be the true one. The universe breathed. It had always breathed. Nothing needed a beginning, because everything was a middle. It was beautiful, and it was almost certainly wrong, brought down not by taste or rivalry, but by two of the most solid discoveries in all of physics. The first killer was subtle. A ghost hiding inside the cycles themselves, spotted as early as the 1930s by a physicist at Caltech who loved the oscillating universe and broke it anyway, because that's what honesty looks like. The second killer, decades later, was the sky itself. But before the funeral, let's take the ride. We've been talking about contraction as a word, a line on a graph, an arrow reversing. Tonight's whole premise is that our Big Bang may have been the end of a universe like ours. So let's do what this channel does. Let's go stand in one and watch a universe close. Come stand on a world in the far future of a closed universe, a planet like Earth circling a quiet orange star, in the era when the great turning has already happened. Gravity has won. The expansion has stopped, reversed. Space has been contracting now for billions of years. Everything tonight in this chapter is real physics. The closed Friedmann solution, run forward honestly. This is what it would actually be like. The first thing to know is the strangest. For almost the whole age of contraction, nothing feels wrong at all. The night sky above you is glorious and calm. Stars rise and set. Seasons turn. Your world's astronomers, though, they know. They've known for ages, the way ours know about the sun's distant future. Where our astronomers measure redshift, the light of distant galaxies stretched by expanding space, theirs measure blue shift. The light arriving from far away is compressed, sharpened, shifted toward blue because the space it crossed was shrinking mid-journey. Every deep image tells them the same thing. Everything, everywhere is on its way back. The galaxies are coming home. And here's a gentle irony worth a smile in the dark. Their sky is friendlier than ours. We spent a whole night, you and I, on a universe where 94% of everything is already unreachable, where galaxies flee over a horizon and are gone forever. Contraction runs that film backward. Distances shrink, light crosses ever easier gaps. Galaxies lost to sight for eons come back into view, like ships returning over a horizon. Their deep field grows richer every era. Their astronomers live in a universe of homecomings. If you didn't know how it ended, you might call it the better sky to live under. Their astronomers, it occurs to me, are the mirror image of the last astronomers we met 2 nights ago, and better off in every way but one. Where the far future of our universe hides its history, carrying the evidence over the horizon until honest science must get the story wrong. The contracting universe performs the opposite kindness. It returns the evidence. Their deep past comes back into view era by era. Their cosmology gets easier, richer, more complete as time runs on. They will know their universe's whole story better than any civilization in it ever did. The one thing the returning light also tells them, with the same clarity, is exactly how that story ends. A sky that hides nothing, including the conclusion. Whether that's a better sky to think under than ours is the kind of question worth falling asleep on. For billions of years, that's all contraction is. A fact in the data, a direction in the light. The sky fills slowly. Andromeda-like galaxies swell and merge with their neighbors early. Collisions come sooner and more often in a shrinking universe, and the night grows gradually more crowded, more magnificent. Generations live and die under that thickening splendor without a single evening of alarm. There's a question their philosophers argue about in the long, calm ages of the closing sky, and it's the mirror of one our own futurists ask. Ours ask, can anything survive the endless cold ahead of us, the dimming, the emptying, the heat death? Theirs ask, can anything survive the warming? Can a civilization ride a contraction down? And the terrible elegance of the closed universe is that the answer is a clean, physical no. Against cold, in principle, you can husband energy, slow your thinking, hibernate across the eons. Cold is a resource problem. But the contraction's heat is not a resource problem. It comes from every direction at once. It is the temperature of space. There is no shade, no insulation, no elsewhere. In an expanding universe, whatever else happens, there is always more room, more future, more away. A contracting universe is the one place in physics where away itself is being repossessed. The real clock, the one that matters, is nearly invisible, the temperature of the sky itself. Remember the cosmic microwave background, the afterglow of the last Big Bang, stretched by expansion into a whisper 3 degrees above absolute zero. In a contracting universe, that stretching reverses. All that ancient light gets compressed, packed into shrinking space, squeezed to shorter wavelengths and higher energies. The whisper begins very slowly to warm. 3 degrees, 5, 10, for an eon or two. This is a curiosity in instruments, nothing more, the coldest thing in nature becoming slightly less cold. But it does not stop, and the arithmetic is patient. Halve the size of the universe and the background doubles in temperature. Halve it again, double again. The fist is closing, and the warmth of every fire that ever burned is still in the room. Skip forward. The universe is 1/100th of its greatest size. The sky between the stars, the black velvet every creature in history took for granted, now glows at the temperature of a winter dawn, close to 300 degrees above absolute zero, room temperature in every direction, everywhere. Night has quietly ceased to exist. On your world, the evening sky is a soft, sourceless amber, the crowded galaxies burning through a haze of sky glow like streetlights in fog. Poets on that world, if there are poets left, write about the last generation who ever saw darkness. And still it closes. The background passes the boiling point of water. Oceans on every world in the universe begin to steam, not from their suns, but from the sky, from everywhere, from the compressed light of 100 billion vanished ages. There is nowhere to hide from it, because it is not a fire in some direction. It is the temperature of space itself. The universe has become a kiln, and everything is inside it. The stars themselves are the last to surrender. For a while, and this is a detail I find almost unbearably strange, the stars keep shining into a sky nearly as hot as their own surfaces, like candles burning in a furnace. Then the background passes them, hotter than a red dwarf surface, hotter than the sun's. Stars stop being able to shed their heat. A star, after all, is an object trying to cool into cold space, and there is no cold space left. One by one, from the dimmest upward, the stars of the universe are boiled apart from the outside, dissolving into the brilliance like ice into warm water. In the final million years, a blink after so many billions, matter itself lets go. Molecules, then atoms, stripped back into the glowing plasma from which they condensed so long ago. And the universe, in its last age, becomes something you've heard described once before in every account of the beginning. A single, seamless, blinding ocean of light and plasma, hotter and denser by the moment, the same in every direction. No structure, no darkness, no cold, everything, everywhere, return to fire. That's the big crunch. Look at your mental picture of the Big Bang's first million years. It is the same picture. The crunch is the bang with the arrow reversed, and now you can feel, not just recite, why generations of physicists looked at the closed universe and thought, these must be connected. The end state of one cycle isn't merely similar to the birth of the next. It is, in every measurable respect, the identical furnace. All that stands between them is a single frame of film, the moment of greatest compression, where the equations tear. And on the question of what happens in that frame, the whole of tonight turns: annihilation or rebound, full stop or turnaround. The oscillating universe said, turn around. always, forever, in both directions, and now, gently, the funeral. Because two discoveries stood up, decades apart, and each of them, in its own way, said no. The first blow came not from a telescope, but from a ledger, and from a man who wanted the oscillating universe to be true. Richard Tolman was a physicist at Caltech in the 1930s, and he did what lovers of an idea should do. He took it seriously enough to do the accounting. The quantity he audited is one we've met before on this channel, the deepest bookkeeping in nature, entropy. The second law of thermodynamics: in any closed system, disorder never decreases, energy spreads, heat evens out. Everything that happens, every star that burns, every collision, every process in every galaxy adds a little to the universe's total of spent, disordered, used up energy. The books only ever fill, they never unfill. Now run the cycles with the ledger open. The universe expands, stars burn, entropy climbs. The universe contracts, everything compresses, but compression doesn't erase entropy. The disorder accumulated in one cycle is still there in the furnace at the crunch, carried through into the next bang. Cycle 2 begins with Cycle 1's entropy already on the books and adds its own. Cycle 3 inherits both. Tolman worked out what this does to the mathematics, and the answer broke the eternal wheel. Each cycle, carrying more entropy, expands further and lasts longer than the one before. The breaths grow. Every cycle is bigger than the last. Feel what that means for the infinite past. Run the film backward. Each earlier cycle is smaller and shorter and smaller still. The breaths shrinking as you rewind, like the bounces of a dropped ball played in reverse, which means they converge. Trace them back far enough, and the cycles dwindle toward nothing, toward a first, smallest breath. The wheel, audited honestly, is not a wheel. It's a spiral, and spirals have centers. The oscillating universe doesn't abolish the beginning. It just pushes it back a few cycles and hides it behind the smoke of the bounces. The question the whole model existed to dissolve, how did it start, walks back in through the front door, carrying the second law like a warrant. Tolman published the problem and left it standing, unsolved. The dream didn't die of it. Physicists are allowed to hope some future mechanism might balance the books. But it walked with a limp from the 30s onward. The ghost in the cycles, entropy remembers. Every bounce carries scars from the universe before. You cannot breathe forever if every breath must be bigger than the last. The second blow, you already know, because we spent an entire night inside it. For the wheel to turn at all, gravity must win. The expansion has to slow, stop, and reverse. Through the whole 20th century, that remained possible. The great question was simply whether the universe held enough matter to close the fist. Then came the 1990s, the rival supernova teams, the standard candles in the deep sky, and the 1998 verdict that rearranged everything on this channel and everything in cosmology. The expansion is not slowing, it is accelerating. Dark energy, the push in the vacuum, the largest ingredient of reality, is flinging the universe open faster with every passing eon. For the oscillating universe, that discovery reads like a death certificate. There is no deceleration, so there is no turning. There is no turning, so there is no contraction, no crunch, no rebound, no next cycle. The stone was thrown not just past escape velocity, but with an engine strapped to it, still firing. The closing sky we stood under a few minutes ago, the blue shifts, the homecoming galaxies, the amber evenings, none of it, apparently, is our future. Our future is the one from our last video together, emptying, cooling, opening forever. So mark the moment honestly, because tonight's story earns its resurrection only if the death was real. By the turn of the millennium, the bouncing universe was dead twice over, killed once from inside by entropy's ledger. The cycles couldn't be eternal. Killed once from outside by the accelerating sky. The cycles couldn't even happen. The most beautiful answer to the child's question lay in the ground with two stakes through it, which is exactly when, physics being what it is, things got interesting. Because in the first years of the new century, the bounce came back, twice, from two directions that could hardly be more different. Once from the mathematics of space itself at the smallest scale that exists, and once from a pair of physicists who looked at dark energy, the killer, and asked the single most contrarian question available. What if the thing that killed the cycle is part of the cycle? The first return of the bounce came from the place the whole problem started, that torn first frame, the singularity. And to understand what changed, we need one honest look at what a singularity actually is, because it is the most misunderstood word in cosmology. When you compress the equations of general relativity toward the Big Bang, the numbers don't just get big. They go infinite. Infinite density, infinite temperature, infinite curvature in zero volume. Popular accounts often present this as a description of reality. The universe began as a point of infinite density. But ask the physicists who work on it, and you'll hear something different, said almost with one voice. Infinities like these are not predictions, they're confessions. When a theory outputs infinity, it isn't describing nature, it's announcing that you've pushed it past its jurisdiction. We've seen it before in physics, theories that worked beautifully until they produced absurd infinities at some extreme, and the infinity turned out to mark, every time, the border where a deeper theory took over. What's missing at the Big Bang's first frame is the deeper theory everyone knows is needed and no one has finished: quantum gravity. Einstein's relativity governs the vast, stars, galaxies, space-time itself. Quantum mechanics governs the tiny, atoms, particles, fields. In almost every situation, they divide the world cleanly and never meet. but crush the entire observable universe toward a point, and the vast becomes the tiny. At the first frame, space-time itself, Einstein's smooth continuous fabric, must obey quantum rules, and nobody fully knows what space-time does under quantum rules. How extreme is the regime we're talking about? The scale where quantum gravity must take over is called the Planck scale, and it lives so far below everything familiar that the usual comparisons give up. The Planck length is to the width of an atom, roughly as the width of an atom is to something like the distance across a great city. Smallness stacked on smallness twice over. No conceivable microscope reaches it. The only laboratory that has ever run experiments at the Planck scale is the universe itself, exactly once that we know of at the moment tonight is about, which is why the first frame stayed a confession for a century. The physics it needs lives 20 orders of magnitude past the smallest thing we can probe. One of the most serious attempts to write that physics anyway is called loop quantum gravity, and its core idea can be said gently: space is not infinitely smooth. Just as matter, zoomed in far enough, stops being continuous and resolves into atoms, so space itself at the unimaginably small Planck scale may resolve into discrete units. Atoms of space, indivisible grains of volume threaded together into the fabric we experience as smooth, the way a sweater feels smooth until you look at the loops of yarn. In this picture, there is a smallest possible pixel of space, and nothing can be smaller, not by decree, but because smaller stops existing, the way half a chess square isn't a place a piece can stand. Now feel what that does to the singularity. Infinite density means everything squeezed into zero volume. But if space is grainy, if there's a smallest pixel, then zero volume is not on the menu. Compression has a flaw. The universe can be squeezed until matter reaches the density of the quantum grains themselves, the Planck density, a number so extreme that writing it out defeats the purpose of words, but it cannot be squeezed past it. The infinity was never real. It was the sound of a smooth space theory being asked about a grainy space world. In 2006, at Pennsylvania State University, 3 physicists, Abhay Ashtekar, Tomasz Pawlowski, and Parampreet Singh, did the calculation that had waited a century. Take a collapsing universe, evolve it with quantum-corrected equations, space made of grains instead of Einstein's smooth ones, and follow it all the way down. What happens at the bottom? The universe does not reach the singularity. As the density climbs toward the Planck ceiling, the quantum structure of space generates something entirely new, a repulsion, an outward pressure, born not from matter or radiation but from the geometry of space itself refusing final compression. Gravity, the great puller, effectively switches sides at the last moment. The collapse slows, stalls, and reverses. Rebound. In the equations, it is astonishingly undramatic. The density rises, touches its maximum near the Planck scale, and comes back down the other side, smooth as a ball at the top of its arc, with time running continuously through the whole passage. No tear, no infinity, no first frame. They called it, with the plainness physicists reserve for their most radical results, the Big Bounce. And notice what the calculation quietly asserts about us. Run our universe's film backward under these equations, and it doesn't end at a wall 14 billion years ago. It goes through the maximum density, out the far side, and into a mirror history, a vast, ancient, contracting universe on its way down. A cosmos that existed before ours, closing exactly the way we watched a universe close a few minutes ago. Amber skies, dissolving stars, the returning fire. Except that its crunch had a flaw, and the flaw threw everything back. Our Big Bang in loop quantum cosmology is not a beginning. It is a rebound, still in progress. Every galaxy racing outward tonight is, in this picture, shrapnel from the gentlest possible collision, a universe bouncing off the bottom of existence. It's natural to ask what, if anything, comes through a bounce, whether anything of the universe before could reach us. And the honest answer has a strange double edge. Structures do not survive. No star, no atom, no arrangement of matter passes through a furnace at the Planck ceiling. The previous universe's every particular, its galaxies, its histories, whatever wondered and watched there, is dissolved beyond recovery. In that sense, the bounce is a true forgetting. But the bounce is not perfect forgetting, and that's the crucial difference from a genuine beginning. The laws come through, the totals come through, and, most preciously for astronomers, the statistics come through. The exact quantum trembling of the final collapse gets folded through the rebound and stamped, faintly, into the newborn universe's pattern of ripples. Not a message, nothing so kind as a message, but a texture. The universe before ours, if it existed, could not send us a letter. It could only leave the grain of its final second woven into our sky's first light. Before the evidence, though, let's finish the journey we started under the closing sky. We stood on a world in the contraction and watched the universe return to fire, and we stopped one frame short of the end. Loop quantum cosmology says that frame isn't an end. So let's cross it. No world to stand on now. Nothing so large survives this deep. So be one last time tonight, a disembodied point of view, adrift in the final second of the universe before ours. Around you is the furnace we left. Plasma, light, everything everywhere compressed past the memory of atoms. The last second unfolds in halvings, the universe halving in size, doubling in fury, again and again, each halving faster than the last. In Einstein's smooth space-time, this ladder of halvings descends forever, to zero, to the tier. But you are not in Einstein's space-time. Somewhere in the final descents, the density approaches the ceiling, the Planck regime. where the grains of space themselves are being asked to hold more than grains can hold. And the universe touches the one thing it has never touched in all its collapsing eons, a flaw. What happens next takes no time at all, and describing it takes longer than it lasts. The quantum repulsion, geometry's own refusal, rises through the crush like a held breath finally pushing back. The halvings slow. The last halving never completes. And with no drama the mathematics can point to, no flash, no impact, nothing but a turn, the greatest catastrophe conceivable becomes its own reversal. The universe's size, which has done nothing but shrink for eons beyond counting, passes through its minimum the way a pendulum passes the bottom of its arc, moving, whole, continuous. Densities begin to fall. Space begins to grow. That's all a Big Bang is from the inside, in this theory. Not an explosion, not a beginning, the bottom of a pendulum's swing. If you had slept through the crossing, and at this hour you'd have every right, you would wake to find nothing changed but the direction, the same furnace, the same fire, now opening instead of closing, cooling instead of heating, on its way to condensing atoms, then stars, then galaxies, then worlds, then, some 14 billion years up the swing, a creature on one of those worlds, lying in the dark, listening to a voice describe the pendulum. You have, in other words, already survived the most violent event in the history of this universe. You were there, every particle of you was, in whatever form the crossing permitted. The bounce isn't only a theory about the deep past, it's a claim about your own ancestry, that the matter reading this sentence to you has been through the bottom of the swing and came out the other side and became a bedtime. Could we ever find the grain of the universe before, the fingerprints carried through? Possibly. And this is what lifts it above beautiful speculation. A bounce is not a clean eraser. The final moments of the contracting universe, its exact unevennesses, the quantum trembling of the crush, would be processed through the bounce and imprinted on the newborn expansion, subtly shaping the pattern of ripples that later became the microwave background's mottling and eventually the arrangement of galaxies. Loop quantum cosmologists have spent years computing what a bounced sky should look like versus a born sky, faint fingerprints at the largest scales where, intriguingly, the real microwave background has long shown small, unexplained oddities. Nothing decisive, whispers, not verdicts. But it is on the sky being argued about in journals right now, which is more than the oscillating universe of the 1950s could ever say. The same honesty we'll owe every idea tonight is owed here, so let it be said plainly. The loop quantum bounce has its skeptics, and their strongest point is a fair one. The 2006 calculation, like most that followed, was performed in deliberately simplified model universes. Perfectly smooth, perfectly symmetric miniatures of the real cosmos. Because the full equations of loop quantum gravity, applied to a realistic, lumpy universe, remain beyond anyone's ability to solve. The bounce emerges robustly in the miniatures. Whether it survives in the full, messy, unsimplified theory is a genuinely open question, and researchers on both sides of it publish regularly. What no one disputes is the central lesson, which stands independent of any particular model. The singularity was never knowledge. It was the smooth space theory's way of saying, not my department. Whether the true first frame holds a bounce or something stranger still, the wall at the beginning of the textbooks was always drawn in pencil. One resurrection then, the bounce reborn at the bottom, from atoms of space. But notice what loop quantum cosmology alone doesn't fix. Tolman's ledger still stands. Entropy still climbs, cycle over cycle, and dark energy still stands. Our universe, rebounded or not, is currently accelerating outward with no turnaround in sight. A bounce behind us is remarkable, but for the full dream, the eternal wheel, breathing forever, someone had to deal with the two killers directly. Someone did, and their answer begins with a word you've been keeping safe since the Stoics. At the turn of the millennium, Paul Steinhardt held one of the most decorated names in cosmology, and he'd earned it in part as an architect of the very theory he was about to challenge: inflation, the reigning story of the universe's first instant, in which space undergoes a burst of expansion so violent it turns a subatomic patch into a cosmos in a fraction of a second. Inflation explains much and it dominates the textbooks, but Steinhardt, watching his own theory evolve, grew uneasy with what it implied and what it couldn't pin down. And there are few things in science more valuable than a founder's doubt. He began to ask whether the universe's smoothness and structure could be explained another way. No inflation, no creation from nothing. In 2001, with Neil Turok and colleagues, he proposed one. They found their central mechanism in the mathematics of string theory, and the original picture is worth pausing on because it is one of the great images of modern physics. In certain versions of string theory, our entire three-dimensional universe, all of space, every galaxy, everything, is a membrane, a brain in the jargon. A vast sheet floating in a higher dimensional space, the way a page floats in a room. And ours may not be the only page. The ekpyrotic picture imagines a second brain, a parallel universe sheet, separated from ours by a gap along a dimension we cannot perceive, and the two sheets are not fixed. They drift, they attract, and periodically, across eons, they collide, two universes clapping together like hands, and the energy of that collision floods both sheets with radiation and matter. That, in this picture, is a Big Bang. Notice the elegance. Because the sheets meet nearly everywhere at once, the bang happens everywhere at once. No center, no special point, the fireball igniting across the whole of space simultaneously, which is precisely what our actual Big Bang looks like in the data, and precisely the feature that puzzles newcomers most. The collision explains it for free. Then the brains rebound, drift apart, cool, grow structure, and begin slowly, inevitably, to fall together again. When they needed a name for a cosmos reborn periodically from fire, they reached back 26 centuries and took the Stoics' own word for it. They called it the ekpyrotic universe, out of fire. An idea first dreamt by philosophers watching Mediterranean stars return to service in the equations of quantum gravity. I promised you that word would come back, and there it is on the title page of one of the most cited cosmology papers of its era. The ekpyrotic model evolved over the following 2 decades, shedding pieces, simplifying, hardening under criticism, into what Steinhardt, working with the physicist Anna Ijas, now calls the new cyclic universe. And this mature version is tonight's second resurrection, because it does the thing that sounds impossible. It takes both of the wheel's murderers, the entropy ledger and dark energy, and puts them on the payroll. Start with dark energy, the discovery that supposedly made cycles impossible. In the cyclic universe, the acceleration we measure tonight is not the universe's final act. It's a phase, a long one. The model lets it run for hundreds of billions, even trillions of years. And its job in the cycle is essential. All that relentless, exponential stretching is the universe cleaning house. Every wrinkle, every black hole, every scrap of structure and debris from the current cycle gets diluted away to effectively nothing. Distances doubling and doubling until the cosmos is smooth, flat, empty, and cold. Dark energy in this picture is not the executioner of the cyclic universe. It's the janitor, sweeping the stage perfectly clean before the next performance. The very observation that killed the old wheel becomes the new wheel's first gear. Then, the turn. In the cyclic model, dark energy is not eternal. Its field slowly evolves, its push weakens, fades, and eventually tips negative, and the universe eases from expansion into contraction. But, and here is the model's quiet masterstroke, not the contraction of our Part 3 nightmare. No collapsing galaxies, no amber skies, no furnace. There's nothing left to collapse, because the janitor already emptied the building. What contracts is an almost perfectly empty universe, and in the mature versions of the theory, it barely needs to contract at all. The heavy lifting is done not by how far it shrinks, but by how slowly and smoothly it does so. An ultra-slow contraction, the ekpyrotic phase, that acts like a great press, ironing space-time flatter and more uniform than inflation ever needed to. This slow squeeze is where the next universe's smoothness comes from. Why should slow contraction smooth anything? Here's the intuition, and it's almost domestic. Wrinkles, in space-time as in fabric, are a competition between the wrinkle and the hole. What matters is whether the irregularities grow faster than the background changes. Inflation wins that competition with speed, stretching space so fast that every wrinkle is yanked flat, like pulling a bedsheet taut in one violent snap. Ekpyrotic contraction wins it with patience. When a universe contracts slowly enough, the energy of the smoothing field comes to dominate everything else so overwhelmingly that lumps, tilts, and wrinkles become irrelevant, rounding errors, less like snapping the sheet and more like pressing flowers, the long, gentle, even weight that leaves everything flatter than force ever could. Two opposite verbs, the same ironed result, which is precisely why telling the theories apart needs the referee we'll meet before the end. Then a bounce, in the modern model a gentle one, at densities far below the Planck extreme, sidestepping the singularity entirely rather than grazing it, and the fire returns. A new bang, a new filling of the empty stage with radiation and matter, a new 13 billion year story of stars. And Tolman's ghost, the entropy that made every cycle bigger, the spiral that smuggled the beginning back in. Watch closely, because this is the most elegant move in the whole design. The new cyclic universe doesn't erase entropy. Nothing can. The second law keeps its books. Instead, it outgrows it. The universe never recollapses to a small size. Each cycle's dark energy phase expands space by such colossal factors that the entropy of any given cycle ends up spread across an exponentially vaster volume. The total on the ledger climbs forever, exactly as Tolman demanded. But the density of entropy, the amount in any region you could ever observe, resets to nearly zero with every sweep of the janitor's broom. Within each cycle, the universe looks fresh, young, low entropy, newly born. Tolman's spiral is still there in the global mathematics, but no observer in any cycle ever encounters it. The scars are real, and they are carried where no one can see them. So assemble the new wheel and look at it turning. Bang! Not a singularity, a bounce. 13 some billion years of light. Stars, galaxies, us now. Then the dark energy age, the acceleration in tonight's actual sky, running for perhaps 1 trillion years, emptying everything. Then the slow turn, the patient ekpyrotic squeeze, the gentle bounce, and fire again. Each full breath, perhaps 1 trillion years or more, breath after breath, after breath, with nothing in the mathematics demanding a first one. The cyclic universe also carries an answer to a question you may have been quietly holding since the contraction chapter, the black hole question. Because black holes are the one piece of debris a naive bounce can't dispose of. Crush a universe full of them, and they should merge, grow, and barrel through any crunch as scars in the next cycle, cluttering the newborn universe with fossils nobody observes. It's one of the classic objections to every bouncing cosmology, and the cyclic model's janitor handles it with the same broom as everything else. The trillion-year dark energy phase dilutes the black holes apart, spreading them so unimaginably far from one another that when the gentle, low-density bounce finally comes, any given region of the new universe is overwhelmingly likely to contain none at all. The fossils still exist somewhere in the global vastness, but like Tolman's entropy, They've been exiled beyond every horizon that matters. The stage isn't just swept, it's swept of monsters. Now, the honest ledger for this beautiful machine, because the accuracy bar on this channel doesn't bend for elegance. The cyclic universe is a minority position. Inflation remains the working assumption of most of the field, woven into the standard analyses, successful across decades of data. The cyclic models bounce, the precise mechanism by which contraction turns to expansion without disaster, remains its most contested joint, argued over in the technical literature year after year. Steinhardt's camp regards it as solved in principle. Many colleagues regard it as a promissory note. What no one disputes is that the model is serious, mathematically explicit, published at the highest level, and, rarest of all virtues in this territory, willing to stake its life on observations, as we'll see before the night ends. And the strangest part of all, the part that reframes tonight's whole story. If this is the true picture, then the acceleration we discovered in 1998, the force we cast as the killer of cycles, the author of the long goodbye from our last night together, is simply the phase we happen to be alive in. The wheel, mid-turn. The exhale, mistaken for the end of breathing by the first generation able to measure the breath at all. Two resurrections then, the quantum bounce rising from the atoms of space, the cyclic universe rising from dark energy itself, and standing a little apart from both, serene and strange, there is a third road to forever, one this channel has walked before, and one whose author would want us to be careful tonight. Some of you were with us the night we spent with Sir Roger Penrose, the Nobel laureate who looked at the other future, the one where the universe never turns around, and found eternity hiding inside it anyway. If you missed that night, it's here on the channel, and it makes a fine companion to this one. Tonight, Penrose's idea needs only a few minutes, not because it's lesser, but because it already has its own night, and because setting it beside the bounce just briefly shows something none of these ideas shows alone. Here is Penrose's road, compressed to its essence. Accept everything the bounce models struggle against. The universe never contracts, dark energy wins forever, and the far future is the endless, cold, empty dark. Wait. Through the evaporation of the last black holes, through spans of time that make everything else tonight look brief, until nothing remains but stray photons. And then notice Penrose's move. Light does not experience time or size. A universe containing only light has, in a deep mathematical sense, no clocks and no rulers, and once nothing can measure scale, scale itself loses meaning. The unimaginably vast, empty end of a universe and the unimaginably small, dense birth of one become, conformally, as the mathematics says, indistinguishable. The same state, wearing two descriptions. The cold, infinite end, Penrose argues, simply as a new Big Bang, no contraction required. The universe passes from eon to aeon not by bouncing off a floor, but by forgetting in the end, how big it ever was. Honesty requires one footnote to the Penrose Road, the same one we gave it on its own night. Penrose believes the previous eon left visible marks, faint rings in the microwave background he calls Hawking points, the evaporation signatures of black holes from the universe before. He has published claimed detections. Other teams, reanalyzing, find the statistics unpersuasive. The argument continues in the journals, unresolved, which is the respectable condition for a claim this large. Tonight's other models would say the same of their own hints. Extraordinary cycles require extraordinary receipts, and every camp is still at the printer. Set the three roads side by side now, and look at what we've actually built tonight. The quantum bounce. The universe rebounds off the graininess of space itself, cycles through density. The new cyclic universe, dark energy empties the stage, a slow squeeze irons it, a gentle bounce relights it, cycles through phases. Penrose's eons, expansion never ends, and the emptied universe conformally becomes a newborn one, cycles through forgetting. And notice the deepest thing the three roads share, because it's the reason all of them exist, and it's a puzzle we've now met from three directions without naming it head-on. The Big Bang was suspiciously tidy. An explosion should be chaos, yet the newborn universe was smooth, ordered, low in entropy to a degree that beggars probability. And it had to be, because that initial orderliness is the capital that everything since has been spending. Every star that burns, every process that runs, every thought you'll have tomorrow draws down the original deposit of order. The one-shot Big Bang has no explanation for the deposit. The universe simply starts freakishly ordered, take it or leave it. And this, remember from his own night, is the very puzzle that drove Penrose to build his eons. Each of tonight's wheels is, at bottom, a machine for explaining the tidiness. Penrose's answer: the forgetting scrubs the books between eons. The cyclic answer: the trillion-year sweep and the slow squeeze iron each new universe smooth. The quantum bounce's answer is the least settled. Its critics ask exactly where the order comes from, but the ambition is the same. The child's question and the physicists turn out to be one question wearing two sizes. Why did everything start so perfectly? Is just what came before, asked by someone with a ledger. Three mechanisms with almost nothing in common, different mathematics, different physics, different fates for the sky, and yet all three converge on the same reframing of the one event every textbook calls the beginning. In all three, the Big Bang is a doorway, not a wall, an event in the history of things, not the start of things. Some of the finest physicists alive, unable to agree on almost anything else about the deep past, keep arriving by wholly separate roads, at the suspicion your 7-year-old self held all along, that the beginning is where our knowledge begins, not where the universe did. And there is a fourth road, the strangest of all, and the best one to hear last, at this hour, when your sense of time is already going soft at the edges. It comes from the physicist Julian Barber, one of the great independent thinkers on the nature of time. And it begins with a question. Tonight has been quietly assuming an answer to, when we say the previous universe came before ours, which way was its time pointing? The direction of time, remember, isn't painted on the universe. The deep laws of physics run equally well forward and backward. What gives time its arrow, as far as anyone can tell, is entropy, disorder, increasing. The future is simply the direction in which things unwind, mix, and spread. We experience time flowing from past to future because we are unwinding along with everything else. Now, every bounce model needs the moment of the bounce to be the most ordered moment. The reset, the smoothed and simplified state from which a fresh universe can unwind. Barber and his collaborators looked at that structure and saw something hiding in plain sight. If order peaks at the bounce, then disorder increases in both directions away from it. On our side, entropy grows toward what we call the future. And on the far side, in the universe before ours, entropy grows the other way. Which means time over there flows the other way. Not backwards in any spooky sense. Inhabitants of that universe would experience their time exactly as we experience ours, flowing from their ordered beginning toward their disordered future. But there, away from the bounce, points opposite to ours. Barber named the idea after the Roman god with two faces. The Janus point, one moment of supreme order, with two universes unwinding from it back to back, each aging away from the other. Each, and sit with this, because it may be the single strangest sentence of the night, each entitled to call the other its past. The universe before ours, in this picture, isn't behind us in some long corridor of time. It's on the other side of a mirror, receding, a twin cosmos whose inhabitants, if any, would say with perfect correctness that the Big Bang lies in their deep past and that the universe before theirs is ours. Whether the Janus picture is right, nobody knows. It lives in the same honest limbo as everything else tonight, but it earns its place in the tour for what it does to the question. The child asked, "What came before the Big Bang?" And the fourth road answers, "Careful. Before is a local custom. There may be no universal past and future at all, only order at the center and unwinding in every direction, with before meaning one thing in this universe and the opposite next door." Of course, the fact that four roads lead somewhere doesn't make any destination real. Beautiful ideas have died all night long in this story, so we owe the wheel one last honest turn, because there is a theorem, proved this century, that walks into every one of these eternal pictures like a bailiff into a party. And what it says and what it doesn't is the right place for tonight's physics to end. In 2003, three physicists, Arvind Borda, Alan Guth, the father of inflation, and Alexander Vilenkin, published a short paper with a long shadow. It's known now by their initials, the BGV theorem, and unlike everything else tonight, it is not a model, not a proposal, not a beautiful guess. It is a theorem. a piece of mathematics proved about entire classes of possible universes at once. What it says, translated gently, is this: take any universe that is, on average, expanding over its history. It doesn't matter what it's made of, what its dark energy does, or what happened in its extreme moments. The theorem is deliberately blind to all of that. Follow such a universe's history backward. The theorem proves the following: you cannot follow it back forever. Somewhere in the finite past, the mathematical description runs out. The backward paths of particles and observers cannot be extended indefinitely. In the theorem's language, the space-time is past incomplete. In plain language, a universe that expands on average cannot have been expanding forever. Something, a boundary, a beginning, a regime where the description fails, sits at a finite distance behind it. Feel the reach of that. It isn't aimed at one theory. It stands at the door of every eternal past cosmology and asks the same question: is your universe, averaged over its whole history, expanding? Because if it is, the past is finite. Vilenkin himself put it about as bluntly as physicists ever do. With the theorem proved, he wrote, cosmologists can no longer hide behind the possibility of a past, eternal universe. There is no escape. They have to face the problem of a cosmic beginning. And before weighing the replies, savor one detail of the authorship, because it tells you how subtle this territory is. The G in BGV is Alan Guth, the father of inflation, and a man who does not believe the universe's past is necessarily brief or simple. He has long taken seriously the picture of eternal inflation, a grand multiverse of endlessly sprouting bubble universes, of which ours is one. The very theorem used in 100 debates to insist on an absolute beginning was co-proved by a physicist who reads its meaning far more modestly. Not reality had a first moment, but this kind of description cannot be extended forever. Something else is needed back there. A theorem's mathematics is beyond dispute. A theorem's meaning is philosophy conducted with sharper tools. Even its own authors do not fully agree on what BGV forbids. So, after everything, does the door close after all? Does the theorem simply win? Here is the honest answer, and it's more interesting than a yes or a no. Every one of tonight's eternal universes knows about the theorem, and each has a considered reply. The theorem has an if the universe is on average expanding, and each model lives or dies by how it treats that clause. The cyclic universe answers, our history alternates expansion with contraction, and everything hinges on the long-run average. Versions of the model tuned one way fall under the theorem's blade. Tuned another way, they may slip it, and the debate over which is honest turns technical and remains genuinely unsettled. Penrose answers, my eons pass through conformal boundaries where the theorem's assumptions lose their grip. The quantum bouncers answer most directly of all. The theorem is proved within classical space-time. Precisely the description we've shown fails at the bounce. You cannot use a classical theorem to bar a quantum door. Each reply is serious. Each is contested. Serious people think the theorem ultimately forces a true beginning behind even the most ingenious cycles. Equally serious people, including authors of the models, think the escape routes are sound. And that, honestly reported, is where the question of forever stands tonight, not settled, but sharpened. A century ago, did the universe begin? Was philosophy dressed in a lab coat. Now it is a fight between named theorems and named mechanisms, with terms precise enough to be wrong, evidence arriving from the sky, and both verdicts still on the table. Either there was a first moment, one dawn with no night before it, a fact stranger than any cycle, or there was not, and the past is bottomless, breath behind breath behind breath, without flaw or first. One of those two sentences is true. Nobody on earth knows which. Your childhood question turns out to be one of the last great open questions in science, and you should feel, lying there, entirely at liberty to have a favorite. Before we close, tonight's ideas deserve what the oscillating universe of the 1950s never had: a scoreboard. Because the deepest change between the old wheel and the new ones isn't the mechanisms, it's that the new ones make predictions and the instruments capable of checking them either exist or are being built. The question of forever has become, quietly, an observational program. Here is what the sky is being asked right now. The first referee is a signal we've never found, and one of the strangest situations in science is that not finding it hard enough would be a discovery. Inflation, the reigning story of the first instant, the one Steinhardt helped found and then left, makes a signature promise. That primordial burst of expansion should have shaken space-time itself violently enough to fill the universe with gravitational waves from the beginning. And those waves should have left a particular faint swirl. Astronomers call it B-mode polarization, twisted into the microwave background. The bouncing and cyclic models make the opposite promise. Their beginnings are gentle, a slow squeeze and a soft rebound shake space-time barely at all. So they predict that swirl is simply not there. At any level the coming generation of instruments can see. Telescopes in the Chilean desert and at the South Pole are hunting the swirl right now, with sensitivities improving year over year. Find it, and the bouncing universes of tonight are in grave trouble and inflation stands vindicated. Keep not finding it, deeper and deeper, and the case slowly, steadily shifts toward the quiet beginnings, toward the bounce. Either way, the sky is speaking. A wheel that was pure philosophy for 26 centuries now has skin in a measurement. The second referee we've already met tonight, the large-scale mottling of the microwave background where loop quantum cosmology's bounce would have folded the previous universe's final trembling. The real sky, as it happens, has shown mild, persistent oddities at exactly those largest scales for as long as we've mapped it, features at the edge of statistical seriousness which might be flukes and might be the grain of the universe before ours. The argument is unresolved and conducted in decimal places. That is, historically speaking, exactly what the early stages of a discovery or of a disappointment look like. And the third referee may already be filing reports. Think back to the end of our last night together, the new instrument in Arizona, DESI, and its tantalizing, unconfirmed hint that dark energy may be weakening. On that night, the hint meant the long goodbye might slow, but notice what it means on this night. The standard picture, the cosmological constant, says dark energy never changes. And if so, the cyclic universe's turn can never come. But the cyclic model requires exactly the opposite, a dark energy that evolves, that fades over deep time as the first movement toward the far future turnaround. For 20 years, that was the model's most awkward, untestable assumption, and now the newest, largest map of the cosmos has come back carrying a preliminary whisper of a dark energy that fades. It is a hint, not a verdict. It may well dissolve in better data, and weakening now does not prove turning later. But for the first time since the Stoics, a measurement exists that leans, however faintly, toward the wheel. Steinhardt's camp noticed immediately, as you'd imagine. If the DSI signal firms up over the next few years, tonight's strangest idea, that the acceleration killing the old cycles is itself a phase of a greater one, will move from elegant heresy to live contender. Watch that space. We certainly will. So the honest scoreboard, tonight, no wheel confirmed, none refuted, 3 separate lines of evidence in motion, and a century-old philosophical question sitting, for the first time in its long life, on instruments instead of intuitions. Whatever the answer turns out to be, we are, by every historical standard, absurdly lucky to be alive while it's being asked properly. Whichever sentence is true, tonight changes the texture of the sky above your house. Start with the dread this channel has walked past twice before. The heat death, the long cold, the last star going out. We've always told that ending honestly. In the standard picture, it's simply where everything is headed, and the only comfort on offer was distance. But every wheel in tonight's story quietly rewrites that ending's meaning. If the cycles are real, the far future's cold and dark is not the universe's death. It's the universe's winter, the emptied, quiet phase that every cycle passes through on the way to its next spring, as necessary to the wheel as the fire is. The heat death becomes the janitor's last sweep of the floor. It's worth being clear that this is a reframe, not a rescue. Nothing of our cycle's particulars survives the winter in any model. But there is a difference, lying in the dark, between a story that ends and a story that turns. And tonight, for the first time on this channel, the turning is a live scientific possibility rather than a wish. Because if any of the wheels turn, the quantum bounce, the trillion-year cycle, Penrose's eons, then look again at everything the universe holds tonight, and notice what it all becomes. A season. The stars. This cycle's stars. The 14 billion years behind us, not the age of everything, but the time since the door last opened, one morning's worth of light in a house older than counting. The atoms in your hands were forged in this breath's stars, but the pattern, the deep laws, the very habit of making stars and worlds and watches, those may be heirlooms, handed through door after door from universes whose whole histories, whose every civilization and ocean and evening ended long before ours began, leaving nothing across the threshold but smoothness and the rules and room to begin again. And if the wheels don't turn, if the theorem holds, if there was truly a first morning, then tonight changes texture the other way. Everything above you becomes not a season, but a once. Either answer, notice, does the same kind thing to this particular evening of your one particular life. It makes it rare. A single turn of a wheel that will never repeat this exact pattern, or a single stretch of the only story there is. You are, either way, inside something that will not come again. And if the cycles are truly infinite, endless breaths behind us, endless ahead, there's one more thought the idea has always carried with it, and it deserves a gentle turn before we close. An infinite series of universes is a great deal of room. Philosophers from the Stoics to Nietzsche have wondered what infinity does to uniqueness, whether, given wheels enough and time arrangements repeat, whether some turn of some wheel unimaginably far along the chain holds another night like this one. Nietzsche found the thought heavy. He called it the eternal return and framed it as the greatest weight a mind could carry. But physics, for what it's worth, leans kinder than Nietzsche did. In the models we walk tonight, each cycle inherits only smoothness and law. The particulars are dissolved at every door, the dice fully rethrown, and nothing compels any pattern to ever recur. Infinite breaths, and each one, so far as anyone can show, a genuine original. If that's the true shape of things, then even in a universe without beginning, without end and without memory, tonight still happens exactly once. There's a reason, I think, that the Wheel of Time is the oldest cosmology we have, older than writing, dreamed on every continent. Nights like this one are why. Breathing is the first thing we ever know, the world swelling and settling over and over before we have words for anything. Waves, seasons, sleep itself, everything trustworthy returns. Of course, we looked up and imagined the sky breathed too. What no Stoic philosopher, no author of the kalpas could have guessed is that 26 centuries later, their intuition would be written down again, this time in equations, with testable fingerprints argued about by people who measure the breadth of the cosmos for a living. The wheel was never proven, but it was never, ever forgotten. Some ideas are like the universe of tonight's story. They don't begin, and they refuse to end. So let the question rest where it wants to rest tonight, unanswered, alive, older than every civilization, and younger than every child who asks it fresh. You don't have to hold it anymore. It has been held for 2,600 years by better rested people than us, and it will keep. Now, as we come to the end of tonight's long walk around the beginning, let's fold it all closed, gently, the way you'd close a book you intend to open again. We started with a child's question and the small click of a door. What came before? We learned that the textbook's wall, the singularity, is not a fact about the universe but a confession of our theories, the edge of a map and not of a country. We watched Friedmann's closed universe breathe and stood under the amber sky of a contraction and felt why the crunch and the bang seemed made for each other. We attended the funerals, Tolman's ledger, which made every breath bigger than the last, and the accelerating sky, which promised no turning at all. And then we watched the resurrections, space itself refusing final compression and throwing the collapse back outward, dark energy, the killer, hired on as the janitor of an eternal stage, and Penrose's eons, cycling through pure forgetting. And at the last, the theorem at the door, the mathematics that may yet force one true dawn behind it all, and the honest verdict that nobody tonight knows. Think about what it means that we can even tell this story. A century ago, we did not know there were other galaxies. Within one human lifetime, we learned the universe expands. Within another, that the expansion accelerates. And now the question of whether reality itself had a first moment. A question that belonged to temples and philosophers for 100 centuries has become a working problem, with theorems and instruments and rival models that stake real predictions on the pattern of the infant sky. The Stoics asked it, watching the stars over the Mediterranean, and answered, fire, forever returning. The authors of the kalpas asked it and answered, wheels within wheels, without first or last. Friedmann asked it with equations, Tolman audited it, and the sky itself weighed in. And we are still asking it, with atoms of space and trillion-year cycles, and satellites reading the first light for fingerprints of a universe before this one. The question has outlived every asker. It will outlive us. And there is something right about that. Because if tonight's ideas are true, outliving endings is simply what everything does. Thank you for spending this night before the beginning with me, from a child's unanswered question to the theorem standing at eternity's door. If tonight's journey moved you or made the word beginning feel less like a wall and more like a doorway, take a moment whenever you surface to like the video and subscribe. It genuinely helps this quiet corner of space keep going. And now, let the whole question go. It doesn't need an answer to be beautiful, and neither does your night. Somewhere beyond the ceiling, beyond the weather, the universe is doing whatever it has always done, opening perhaps for the only time, or breathing perhaps, one breath among endless breaths. Either way, it isn't finished. Either way, you're inside it, warm, with time still running gently through the room. And if the wheel does turn, then somewhere unimaginably far ahead, in a universe not yet born, on a night not yet possible, someone may lie awake under new stars and ask what came before everything. It will be a good question. It always was. Sleep well.